For any function, if you write the equation for the tangent line to the function at some particular point, and then graph the tangent line and the function, and then zoomed in, eventually it would look like you zoomed in on the same straight line. The linearization is really just the tangent line equation, which we can use as an approximation for the function. Because that tangent line is such a good approximation, it's such a close fit for that function near the point of tangency, we can use it to actually approximate the function. So, start with point slope formula. Y minus y1 is m times x minus x1. If you took that equation, and since we're thinking of writing a tangent line equation, instead of thinking the slope, we're going to think f prime. And instead of thinking x1 and y1, we're just going to think some input value. So pick a number, pick a value for x, and then the y that goes with it is going to be, if the input value, we're going to call it a, then the output that goes with it is f of a. This is all the same as point slope form. We're just using slightly different notation. So if I'm going to use f prime of a for the slope, and a and f of a for the x1 and the y1, then I get this equation here. Y minus y1 essentially is equal to the slope, f prime of a, times x minus x1 is a. If I isolate y, just by adding this f of a term to the other side of the equation, I have a function. And that function we actually call the linearization of f at a. You can think of it as a function of x. If you plugged in some x value, you could get a y value. It's a y value on the tangent line, it's not a y value on the actual function. It's going to be pretty close to the actual value of the function. And here, we call it the standard linear approximation of f at a, just because you could use a bunch of different lines to approximate functions in different places, but the best approximation is going to be the one that's the tangent line approximation, so the tangent line formula with the y isolated. Once you have a linearization function written, you can use it to approximate values of the function f, as long as the inputs you are interested in are pretty close to the input value that you used as the point of tangency, the x1 in your x1, y1 that you used in the point slope form. And then how good that approximation is depends on how close your input value is to the point of tangency that you chose. So just to make the point here, the linearization function, it's really just point slope form for the equation of the tangent line with the y isolated. So if you want to memorize this formula, that's fine. If you want to just think of writing the tangent line equation in point slope form and then isolating y, you're going to have the same experience, you're going to have the same answer. So whichever one works better for you is fine. In fact, I'll do this example both ways. So here, find the linearization of the function cosine of x at the place where x equals pi over 2. And I'm going to use it to find an approximate value for cosine of 1.75 without using my calculator. So here, I'm going to start with the point slope form for the equation of the tangent line, just because even if you forgot this formula, you could always go back to that. So if I want the equation of the tangent line, I'm going to write y minus, what's y1 going to be? It's the y I get when I plug in x pi over 2 for the x. So f of, that's an f, pi over 2. That's the same as cosine of pi over 2, which is 0. Is going to equal, I need the slope. What's the slope of the cosine function when x is pi over 2? Well, that's going to be f prime of pi over 2. What's f prime of x? F prime of x, the derivative of cosine is negative sine of x. I ran out of room. So I need the negative sine of pi over 2. Sine of pi over 2 is 1, so I'm going to have negative 1 as my slope. I'm going to have x minus pi over 2. So I sort of lucked out here because now when I go to isolate y, it doesn't really take any work. I had y minus 0, so I would say that I could use the function y equals negative x minus pi over 2 as my linearization, as a function, as a linear function that approximates the cosine function near that place. Okay, so let me erase this. And let's just prove I get the same thing if I was going to memorize this linearization formula. So I'm going to write L of x is going to equal, what's a in this problem? Well, it's the input value, the x value of the point of tangency. So f of a, which is what I get when I plug pi over 2 into the f function, which is 0, plus f prime of a is the slope of the cosine function when x is pi over 2. Well, what's the slope of the cosine function? We said a second ago f prime is of x is equal to the opposite of sine of x. So when I plug in pi over 2, f prime of pi over 2 is going to be the opposite of sine of pi over 2, which is the opposite of 1, times x minus a, in this case, pi over 2. So you can see that this function happens to be written in function notation, but is exactly the same as the y function I got when I did this just using point slope form. So now let's actually answer their question. We need an approximation for cosine of 1.75, and I want to get it without using my calculator. So just notice, what do we know about pi over 2? So pi is 3.14159. Half of that? Half of 3, but a little bit more. So a little bit more than 1.5. That's why it's okay to use this approximation to try to get an approximation for cosine of 1.5, because 1.5, that input value, it's pretty close to pi over 2. So I'm going to write here, and watch the notation. L of 1.75 is going to equal 0 plus negative 1 times 1.75 minus pi over 2. And remember the whole idea from that first part of the slide, and this is on your paper too, checking it's on your notes paper. I don't actually know the cosine of 1.75 now, but I do know that cosine of there's no primes here. So f of 1.75, which is the same as saying cosine of 1.75, is approximately equal to, that's got to be an approximately equal to, L of 1.75, which is equal to, what is this? If I distribute that, that's pi over 2 minus 1.75. All right, so just for fun, I used my calculator to evaluate pi over 2 minus 1.75. I got negative 0.17920. And I will use my calculator to find the cosine of 1.75 cosine, and that's negative 0.17824. Pretty close.